Hello, this is Concrete Path, and today's lecture is about the final topic of SOM, that is your thin pressure vessels. Thin pressure vessels. So we say that you have a cylindrical vessel, let's say you have a vessel, and the thickness of that if the thickness is very less, if the thickness is, let's say there's some diameter, inner diameter d, and there is also some thickness of t. So if the thickness is that it is almost I would say d by 10 to d by 15, it's less than these values. So I would say the thickness, that the shell, thin pressure vessel, or we can say shells also. So the shell is thin shell, we can say thin shell. Now in this vessel there might be some fluid inside. There might be some fluid, and because of fluid we have that hydrostatic stress, that hydrostatic pressure. We do know that pressure of intensity P, let's say the pressure, and it's because of this hydrostatic stress, because this it's P in all directions, so it's action of stress is in this way. So at a point it's acting in different directions. So this is your state of stress for that fluid inside the material. Now because of that fluid pressure, because of this fluid pressure, in the material itself, material has developed three kinds of stresses. So one is that what we call as Hope stress. Second one is that we call that as longitudinal stress, and third one is that we call that as radial stress. Let's say that this is your section 1-1, and this is your section 2-2, and if I cut that section 1-1, I would say this is your vessel, part of the vessel, and for the length of L, this is your material. And I would say you cut the section, and inside there there is a fluid pressure. Let's say the fluid pressure is in this fashion, fluid pressure P. This is your fluid pressure, inside pressure. So this is your P pressure. And I would say one of the stresses that we call as Hope stress, that's also we call that as circumferential stress or meridional stress. So this is your Hope stress sigma h. So it's along that periphery of that material in that thickness T, on both the sides, we can say. This is your sigma h. If for the pressure inside, we say this sigma h is tensile. For inside pressure. If the fluid is inside, we say for fluid pressure inside, the stresses developed in the material is tensile. And so let's take that. Now if you want to say what is the value of that Hope stress, what is the value of that Hope stress? We do one assumption. So for the calculation of Hope stress, if I write sigma Hope calculation, so we assume that the pressure, inside pressure, is acting perpendicular. It's not in different directions. We assume that it's not in the different direction. We assume that P is actually perpendicular to the projected area of that section, So if you cut that section and there is some diameter d, if there is some diameter d and there is some length of L, so we say that if you take that projected area, if you take this projected area now, so if you take this projected area of dimensions, d and L, and we say that the pressure the inside pressure, fluid pressure is acting perpendicular to this, and it's not in different directions. So it's only in one particular direction. This is assumption for the calculation of Hooft stress. So you have to keep that in your mind, that we assume that Hooft stress calculation, for the Hooft stress calculation, we take that P perpendicular to projected area, projected area. So if I equate that, if I write that summation of forces in y direction, when I write that summation of forces in y direction, I say that Hooft stress is acting on two different, on these two, what you call as on these two sections of thickness D and L from both the sides, D into L, and it's balancing that downward stress of what we call as pressure into that area. So if I write that pressure into area of D into L, that we equate with the Hooft stresses for this area of 2 times thickness into L. So your Hooft stress becomes equals to PD by 2T. Hooft stress is pressure times inner diameter of that vessel divided by twice the thickness of that vessel. So this is your first kind of stresses. And on that, when you cut this section, so we said that on this section where sigma h is acting, there is no shear stresses developed on that section. Tau is 0. So we say your Hooft stress is a principal stress. And we say that it is tensile for if the pressure is inside, if the what you call as fluid pressure, it is tensile for fluid pressure. And for the outside pressure, if you're talking about outside pressure, that means inside there is no pressure, inside there is no fluid, but from the outside there is some pressure outside. If you're talking about for the outside pressure, and for that the stresses that would get developed on that material cross section, that would be compressive in this fashion. That would be compressive because your stresses are tensile. That means in this way, because your P is outside, P is in this way, so your sigma hoop would be compressive, minus PD by 2T for the outside pressure. Now let's talk about that second kind of stress we said, that's longitudinal stress. Second is your longitudinal stress. So if I cut this section 2-2, if I have this section 2-2 and I want to see what's happening there. So if I cut this section, I would say you are applying some stresses inside, pressure is there, inside pressure of P is there from all directions. So inside pressure is there, P, and it's acting for this area, inside area of that pi d square by 4. But actually it's stress in this way. It's stress in different directions. So here we have, if I write that sigma longitudinal calculations, there we have assumption that this what we call as because of that stress inside pressure, P inside is acting, we say that P inside is acting on projected area of that, projected area. So that means we assume that P inside is also perpendicular to projected area of that inside diameter D. There's some inside diameter D on which your stress pressure is acting, inside pressure. So this is your projected area of I can say projected area AP equals to pi d square by 4. On that, P is acting perpendicular is that to that cross section, normal stress. So that should be balanced. It should be balanced by I would say longitudinal stress. There should be some longitudinal stress. Along that thin section, along the long axis. I would say if you're talking about that in the main section, I would say the long section would be in this way. That longitudinal stress would be in the direction of long axis. Longitudinal stresses in this way. So when we equate that summation fx equals to 0, we write that this longitudinal stress is acting for this thickness. So there is some thickness. There's some thickness. There's some thickness of. So on this one, where our stress of sigma long is acting, sigma long. So if we calculate that, what should we? How should we calculate that? So there's some thickness and there's some diameter, but inside there is hollow. So we can take mean diameter. If we take d mean, that would be equals to some value of d plus from this side we go to thickness by 2, from the other side you go to thickness by 2. So there would be some mean diameter of that. So you take that mean diameter, that is d plus t. So if I write that, what should be the area of that strip, what we call as main strip. So there is some main strip. There is a mean strip with the mean diameter of dm equals to d plus 2t. And if I say what is the area of that, area of that shell or strip, that would be equals to 2 pi r into thickness of t. Similarly, we can write pi dm into t. So this is your area of that shell. And if I write that pi into dm, value of dm was equals to dt, d plus t into t, thickness of t. So this is your area, and it's having that stress of longitudinal stress sigma long into a. So if I equate that, summation of fx goes to 0, I will write sigma long into pi d plus t into t. That should be balancing that inside pressure of P into that pi d square by 4. P into pi d square by 4. P into pi d square by 4. P into pi d square by 4. That means I would get a value of pi dt plus pi t square equals to P pi d square by 4. And there was some stress also somewhere. Yeah, stress is also there. Stress into stress. So we say that your thickness is very, very less. So we say that pi into t is, we say that d into t, yeah, we say that t square is very, very less as compared to d into t, because there is some diameter, but the thickness is very less. So this can be negligible. This is negligible with respect to that of dt. With respect to dt, I would say that we can say finally sigma times pi dt equals to P times pi d square by 4. Pi d square by 4. So we can write the final equation that sigma long equals to PD by 4 times thickness. And in this case also we say tau is not there acting, no tau is acting, so we say that this is also principal stress. And if I have that sigma hope was equals to PD by 2t, and this value is PD by 4t. If this value is 100 megapascal, and this one would be 50 megapascal. So that means Hope stress is dominant in this one. In the vessels we have Hope stress that's dominant. Now third one is that what we have radial stress. So it is along the radial direction. If you have this cross section, I would say there is some pressure acting, and in the same direction of pressure. So if you take any section, if you take any arc of that section, if you take this section, I would say there is some center and pressure is acting in the direction of that inside pressure. So we say that radial pressure is equals to minus times P. If pressure is in this way, so in the same direction we say radial pressure is acting. So radial pressure is along that same direction. So this is our direction of radial pressure. So third one is that radial pressure equals to minus times P. Minus times P, compressive. Minus times P, that's compressive. So we got these three different kinds of stresses. Now because of stresses, we can say in the material there is development of strains also. So strains would also get developed. If we have those equations, I would say you calculate the strains now. Let's take that strain, what we call as Hope strain. That Hope strain we can write EH equals to sigma Hope minus mu times sigma long by E, and minus times mu sigma radial by E. And if we because your sigma radial is, we say this part is because that one thing is that we say sigma radial is negligible with respect to these other two values. This is negligible. So if you remove this part till now, I would say your sigma hope would be equals to, yeah, strain in hope direction would be equals to sigma in hope was equals to PD by 2T minus mu times sigma log was PD by 4T divided by E. So you get a value of that PD by 4T 2 minus mu, and you have this E. So if you ignoring this part for calculation, if you ignore this part, so you got that strain in hope is equals to this one, and we know that strain hope that hope stress is along that circumferential direction, that's along that circumference or meridian. So I would say that that would cause that change in diameter, so you can write delta d upon d, change in diameter by original diameter, that is hope strain. Now if I account that value of that radial pressure also, if I account that effect of radial pressure also, I would say your hoop strain would be equals to PD by 40 E 2 minus mu, and you have that minus times mu, and sigma radial is minus times P divided by E. So finally you can write plus mu P by E. This is the extra part we can have from this one, plus times mu P E by E, mu P by E. Now second one is that longitudinal strain, E longitudinal strain, you can write EL, that equals to sigma long minus mu sigma hoop by E, and for if you count that part of that also, we can write directly minus plus mu P by E. So this part you have this extra part, you keep that in aside. For this part we are going to study, so I would say E long equals to, what's the value of longitudinal stress? That was PD by 2T, and this one was your PD by 40. PD by 40 and PD by 2T. So we can write PD by 40 minus mu PD by 2T divided by E. So we can get a value of PD by 4TE 1 minus 2 mu. So this is your value of that longitudinal strain. And if you account that effect of radial pressure also, you can get PD by 4TE 1 minus 2 mu plus mu P by E, effect of that radial pressure also. So we got these strains. Now because we have strains, we have normal strains, so we can have what we call as change in volume. We can have also change in volume also, because your normal strain is called normal stresses cause normal strains, and because of normal strains we can have volumetric change. We can have change in volume, that we have volumetric strain. So that we can write your volume is equals to, for this cylindrical shell, we can say volume equals to pi d square by 4 into L, pi d square by 4 into L. And if we talk about the change in volume, delta V, I would say you have these two variables, one is your D and one is your L. So if I vary those, I would say, so I differentiate that those two variables, I would say 2D into value of L, and you have that differential of small d, plus similarly you can write that d square and differential of that length L, dou L. Now you got this change in volume. If I write that, what is the value of strain, volumetric strain, that is delta V by V, that equals to pi by 4, that is 2d L dou D plus d square dou L, and divided by pi by 4 d square L. This part goes, and this for the inner part we can get value, so some value of 2 times dou L by L yeah, 2 times is it yeah, it's not dl, it's d times L. It's not dl, I would say. This is d separate, then L, d separate then L, or we can directly write in terms of that. If I write that if I write that dou d first, that it might get easier for you. This is your 2d, then internal differentiation of dou d and length of L. Similarly from this side, d square and internal differentiation of dou L. Internal differentiation, that is dou L. Yeah. So similarly, you can write here also. You can write here also. You can write in this fashion also here, such that confusions are not arising. 2d dou d L. 2d dou d L. So we can write 2 times. You can write 2 times. Your d by d gets cancelled, so you are left with dou d by d, and L goes cancels. This L and this L goes cancels, so you are left with 2 times dou d by d, and in the second term you are left with that d square goes, so you are left with dou L by L. So your volumetric strain, that equals to 2 times, what is this strain? We call it as a Hooft strain, and this one we can call it as a longitudinal strain. So we can get the equation that volumetric strain equals to 2 times Hooft strain plus longitudinal strain. Now, if you wanted to have that effect of radial what do you call as, now if I substitute the values of EH and EL, I can say EV equals to 2 times, what's the value of E hoop we have? What's the value of E hoop we have? Value of E hoop we have. That's PD by 4TE, and effect of this one is also mu P by E. So this part is your PD by 4TE 2 minus mu. So you got this part, and plus longitudinal strain equals to PD by 4T 1 minus 2 mu. Okay, now we can take few terms common. We can have some terms common. Then we can have volumetric strain equals to PD by 4TE. That is 4 times 2 to the 4 and 2 mu. Then we have from this side plus 1 minus mu. So you can get a value of 4 plus 1, that is 5. 5 minus 2 minus. Is it 1 minus mu? Is this 1 minus mu? Yeah, this is 1 minus 2 mu. This is 1 minus 2 mu. So you can get a value of 4 minus, that's 4 plus 1 is 5 minus 4 mu. So you got finally that strain, volumetric strain equals to PD by 4TE, then 5 minus 4 mu. So this is your final result. And if you want to account that effect of radial pressure also, you can write in the first part we have E hoop, that is 2 times. So in that effect we can have 2 times mu P by E, and in the long strain we can have mu P by E. So finally you can have 3 times mu P also, 3 times mu P by E also in that. 3 mu P by E, 3 mu P by E, effect of that long radial stress also. Now we got these. Now next topic is that tau max, maximum shear stress. How much maximum shear stresses we can have? We have 3 normal stresses acting in different, that we also have that we can say they are the principal stresses. One is your sigma radial, that is negative minus P, and one is your sigma hoop, that's your sigma 1 we can say, and third one is that sigma long, that's your sigma longitudinal, PD by 2T, PD by 4T, this is your PD by 2T. And I can say, if you talk about tau max in plane of sigma hoop and sigma long, if you talk about that plane in which sigma hoop and sigma long is acting, so I would call that, so then I would say your tau max in plane would be equals to, that is sigma 1, sigma hoop minus sigma long divided by 2, because your sigma 1 is major, So I would write sigma hoop minus sigma long by 2. That's PD by 2t minus PD by 4t divided by 2. So finally you can get a value of PD by 8t. PD by 8t. Tau max in plane. Now, if you're talking about that absolute, if you're talking about tau max absolute, tau max absolute, tau max absolute, that is, we know that tau max absolute is sigma 1, sigma max minus sigma min by 2, comma, sigma max by 2, or sigma min by 2. Or we can say sigma 1 by 2, sigma 2 by 2. Mod of these three. That's maximum out of these three. So if you're talking about that, if we have these, one is your P minus P, next one is that PD by 2T, and third one is that PD by 2T, second one is that PD by 4T. So this is your sigma radial, sigma long, sigma hoop. So we can say this one is your sigma 1, this one is your sigma 2, this one is your sigma 3. Now I would say if you take maximum out of these, I can write that PD by 2T minus of sigma minimum. This is your sigma minimum, that is sigma 3. That is your minus P. This is your sigma 3 for the absolute case. So you can write minus times minus P divided by 2. Second one is that we can directly say sigma 2 is lesser, so this value is lesser, so we can write sigma max by 2, sigma 1 by 2. So we can write PD by 2T and divided by 2. So out of these two, we can have the value that is maximum. So we can get from the first one, we can get PD by 4T plus P by 2, and from this one we can get PD by 4T. So we can say clearly that this value is maximum. So we can write tau max absolute equals to that PD by 4T plus P by 2. And sometimes you can ignore that P by 2 also, but keep that in mind that this is your extra part of P by 2. So tau max in plane was equals to PD by 8T, but your absolute is PD by 4T. That's twice that of that initial value, and you have also some term of P by 2. Now if you want to represent that in terms of Mohr circle, I would say that you have that reference line. There's some tau, there is some sigma, there is some sigma. I would say let's take that value sigma 1 equals to PD by 2T. Let's say that value is 100 megapascal, and sigma 2 is PD by 4T, and that is 50 megapascal, and sigma 3, that is radial, that's minus P. Let's take that as minus 20. So for the tau max in plane, we are talking about that only these two values, sigma 1 and sigma 2. So if you have this sigma 1 and if you have this sigma 2 somewhere here, if this is 100, 50 would be somewhere here. So sigma 2. Now if I write that radius equals to tau max, that's also tau max in plane. Can I get that value? Sigma 1 minus sigma 2 divided by 2. That's also PD by 80. So if I have those values, I can write 100 minus 50 by 2, that is 25. So a radius of 25, that means radius of 25. And if I calculate that center, I would say center is at sigma 1 plus sigma 2 by 2. That's 100 plus 50 by 2, that is at 75 from the origin. So center would be somewhere here, and you draw a circle of radius 25. So there is some tau max here. You can say this is your tau max in plane. Tau max in plane. Now, if you're talking about tau max absolute, so I would say there is some 100. Sigma 1 is some sort of 100, let's say, and sigma 2 is some value of 50, and sigma 3 is some value of minus 20. Now, for the tau max absolute, I would write for the maximum tau I can have, maximum radius I can have, R max. For that I can take the extreme values. I can say 100 minus 20 divided by 2. That is radius of 60. And to calculate the center, I would say center would be at 100 plus sigma 1 plus sigma 2 by 2. Sigma 1 plus sigma 2 by 2. Or we can say sigma 1 minus sigma 1 plus sigma 3 by 2. Sigma max plus sigma 3 by 2. Sigma max plus sigma min by 2. So finally 40. So center is at 40. So center is somewhere here, and radius of 60, and radius of 60. So that means you have to make a circle. You have to draw a circle connecting these 2 points. So I would say there's some center C, there's some center C. I would say there's some center C from the origin at a distance of what we call as sigma hoop minus sigma hoop plus sigma radial by 2. This is your center. So, and at that value we can have some tau max. This is your tau max absolute. Tau max absolute equals to, I would write tau max absolute equals to sigma hoop minus sigma radial by 2. That is equals to PD by 40 plus P by 2. PD by 40 plus P by 2. The value for that we took that value 60. So that's your 60. And that's your tau max absolute. So that was the end of this concept we have from the cylindrical thin vessels. And now similarly we have spherical vessel also. We have spherical vessel also. Spherical vessel also. Spherical vessel. So for the spherical vessel, if you talk spherical thin vessel, the cylinder was in this fashion. And a spherical vessel is it is some sort of circles. So for that we say that your stress that gets developed is hoop stress in all directions. Hoop stress gets developed. So if you have any section, if you take any section, I would say, let's take another way. I would say you cut any section, and there is your vessel, spherical vessel. I would say you take any element, on that your sigma hoop is acting in both directions. Here we say that sigma 1 is equals to sigma 2. Sigma 1 equals to sigma 2. If I calculate that, I would say there is some pressure, but I would assume that, if I assume that the pressure is actually acting perpendicular to the projected area, I would say P is acting for the area pi d square by 4, similar to what we did in case of cylindrical vessels, and that should be balanced by that sigma. On that thickness of mean thickness of pi times d plus t into some thickness of t. So this is your mean perimeter and thickness of t. So then accordingly we can say that d square we can ignore, because it is with respect to that dt it is lesser. So finally, similar manner we can write your sigma equals to what we call as PD by 40. Here we say that sigma 1 is equals to sigma 2 is equals to PD by 40, and we say that what should be the value of tau max in plane, and that value equals to sigma 1 minus sigma 2 by 2, that is 0. And tau max absolute, you can also calculate tau max absolute, that is sigma 1 plus sigma 2. Yeah, that is sigma 1 minus sigma, sigma 2 by 2, comma sigma 1 comma sigma 1 by 2. Maximum out of these, that is, we can say 0. Out of this 0 and out of PD by 80, we can have maximum value of PD by 80. So this is your tau max absolute. This is tau max absolute for this thin spherical vessel. Tau max absolute. And tau max in plane equals to 0. So if we're talking about that what should be the value of that Hoof strain? Hoof strain, what should be the value of Hoof strain? The value of Hoof strain would be equals to sigma hoop minus mu sigma long by E. And we know that sigma is equals to sigma hoop is also equals to that sigma, and sigma long is also equals to sigma. That's sigma minus mu sigma divided by E. So finally we can write PD by 40 divided by E 1 minus mu 1 minus mu. So this is your hoop strain, PD by 40 E 1 minus mu. Then you can also calculate volumetric strain. I would say volumetric strain can be calculated from the change in volume by original volume. So if the initial volume, we can say 4 by 3 pi r cube. So we can write pi d cube by 2 to the 4 6 pi d cube by 6. This is your initial volume. And if I want to get the value of delta V, that is equals to pi by 6 of 3 times d square and differential of that d, dou d. So divided by d, divided by volume, that we get pi by 6 of d cube. So we can get that. Finally, we can write volumetric strain would be equals to 3 times dou d by d. So change in diameter by original diameter, that we can say that is strain, hoop strain. So that is E times hoop strain. So 3 EH we can write that. So we can write that 3 times EH. So 3 by 4 of P d by dE 1 minus mu. So this is your volumetric strain. Volumetric strain is 3 by 4 of PD by dE 1 minus mu. So let's take the problem. Let's take the problems. Let's take the problem 1. You have a cylindrical vessel, cylindrical shell. You have a cylindrical shell of 0.8 meter dia. So there's some shell of diameter 0.8, and there's also mentioned that thickness of that shell equals to thickness of wall 10 millimeter, and it's subjected to internal pressure of 2.5 megapascal, internal pressure, fluid pressure. And you need to say change in diameter, change in length, change in volume, These are your changes of dia, length, and volume changes. You need to calculate those, and you have the data of E equals to 200 gigapascal, Poisson ratio of 0.25. Now, since it's a cylindrical vessel, we need the length also. So there's some length also. Length of 3 meter. So if I write that equation, I would say for calculation of diameter, I would say we need to calculate that hoop strain. Do you know the equation for hoop strain? Is it PD by 4TE and 2 minus mu, 1 minus 2 mu. That's 1 minus 2 mu, 1 minus PD by 2T, Yeah, some value is there, but we also know we also can have that in this way, sigma hoop minus mu sigma long by E. In this way also we can do, or either you can take in this way also. If you use that equation of PD by 4TE, then you have to say PD by 4TE, then you multiply that PD by 4TE, the equation we have for the hoop strain. Either you can calculate first hoop stress, longitudinal stress, then you substitute in this equation to get this hoop strain, or directly you can use that result we have derived, that is PD by 4TE, and some factor is also there inside. Yeah, we have not derived any. That was for the volumetric strain we have derived with the equation. You can calculate the values of hoop stress and hoop longitudinal stress. Let's calculate those. we have that PD by 2 times thickness. So we have the value of hoop stress equals to 100 megapascal. So longitudinal stress would be half of that, because it's PD by 40, so 50 megapascal. So now you can say what should be the value of hoop strain. Hoop strain equals to 100 megapascal minus 0.25 times 50 megapascal divided by value of E was your 200 gigapascal. So your value of hoop strain, you got the hoop strain value. And once you got the hoop strain, you can say that hoop strain equals to change in diameter by original diameter. So your change in diameter would be equals to hoop strain times initial diameter. So initial diameter was 800 millimeter. So your change in diameter would be finally equals to 0.35 millimeter, and it's increased because your stresses are tensile. So your strain developed or change in length, change in diameter would be that increase of diameter, 0.3 millimeter, 0.35 millimeter. Now second one is that hoop strain, longitudinal strain, EL. And from that EL, that would be equals to delta L by L. So we need to calculate delta L. So delta L would be equals to EL into L. That's the value of EL would be equals to sigma long minus mu sigma hoop divided by E and length of L. So you have those values of long and hoop. So this is your 50 minus 0.25 times 100 divided by value of E is equals to 200 gigapascal. So multiply the length of L. What is the value of L? 3 meter, 3000 millimeter, 3000 millimeter. So you can get the value of change in length, that is equals to change in length is 0.375 millimeter. Change in length is 0.375 millimeter. Now third one is that change in volume. So we know that change in volume is equals to hoop stress 2 times hoop strain plus 1 times longitudinal strain. So you can say 2 times, actually that equation is not change in volume, that's volumetric strain. So volumetric strain is 2 times hoop strain plus 1 times longitudinal strain, and that value is equals to final value of 1.25 10 to the power minus 4, and that is equals to delta V by V. So change in volume, we can say change in volume would be equals to volume times this volumetric strain. So if I substitute the value of volume, what's the volume? We have cylindrical shell having this diameter of d, so we can write pi d squared by 4 into length of L, 3 meter and diameter 0.8. So pi by 4, 800 square square, length of 3000 millimeter into that volumetric strain of 1.25 10 to the power minus 4. So you can get the value of increase of volume would be equals to 10 to the power 3 millimeter cube. So this is your increase in volume. Let's take problem second. Let's take the second problem. Let's take the second problem. You have a copper tube. There's some tube. So we have a diameter of 50 mm and length of L equals to 1200 millimeter, and thickness of wall equals to 1.2 millimeter, and the tube is closed from the both sides. So the ends are closed. We write ends of that tube are closed. And one thing is that now before ends are closed, you had to fill it water. Water was filled with what we call as entire. For the entire volume, water was filled at the rate of atmospheric pressure. initially the water was applied, and there was atmosphere, the pressure inside was maintained as equals to outside pressure. So internal pressure was equals to outside pressure. P ATM was from this side and P ATM was from inside also. Outside pressure was equals to inside pressure, P ATM. Now the thing is that we need to say what is the increase in the pressure. So the problem is that what is the increase in pressure? What is increase in pressure? What is the increase in pressure when additional volume? So we added one extra part of water, extra water volume of 32 cubic centimeter was pumped into the water, pumped into that what you call as tube. So initially there was water, and inside pressure was equals to outside pressure. So inside pressure was initially the inside pressure was equals to atmospheric pressure. And so if I say that initially the pressure was inside, that was P ATM. So because of that, there would be development of Hooke's strains, Hooke's stresses, yeah, longitudinal strains, longitudinal stresses. Can I say that? But based on the fact that outside pressure would be also there, but because outside pressure would be also there, that's also ATM, P ATM. So for the outside pressure, your longitudinal strain, yeah, for the Hooke strain would have been compressive, and for the inside pressure, your Hooke strain would be tensile. So finally, net value would have been 0. Hooke stress 0, longitudinal stress 0 for these conditions. But once you added extra water, there would be an increase of pressure. Now you need to say, because we added extra volume of 32 cubic centimeter into the water, into the tube, you need to calculate what should be the increase of pressure that gets developed. And extra details are that you have that material of the copper. Copper is equals to 100 gigapascal, and that bulk modulus, what you call is it bulk modulus? Yeah, bulk modulus of elasticity is your 2000 Newton per millimeter square, and Poisson ratio 0.3. So we have this data that what is the thickness, dia, and length of that material, and its materials, those materials characteristics also, that what is the E, mu, K. So we have all this data. So we need to say, how can we get this increase of pressure because of increase in volume of water, addition of that extra water. We say that what's going to happen, that you add inside pressure, you add some extra pressure you add some extra water is added. So because of that, inside initially there was water, and there was some material. So there was some material. That means if inside pressure has to get developed, if the inside pressure has to get developed, that means inside that, because of that, there is development of Hooke stresses and longitudinal stresses, and because of those stresses, there is development of strain. And because of that strain, Hooke strain, longitudinal strain, we can have volumetric strain. Because of volumetric strain, we can have change in volume. And similarly, because your water, we can say it's also getting compressed. We can say there is water might be having compressibility. So it is having that compressibility of dou V by V equals to P by K. That's strain equals to stress by K. So that's decrease of volume. That's change in volume is decrease. The decrease of volume with increase of pressure divided by K. So we can say that the volume we added, the extra volume we added, volume of water added, that would be equals to increase of volume of what we call as increase of volume of material, plus decrease of volume of water because of compression. So if I take those, so if I calculate that, what is the increase of material? What is the volume increase of material? So I need to calculate that. That's E times volumetric strain into volume, total volume. So that is equals to volumetric strain into total volume. So that is the change of volume of material, plus what is the decrease of volume of water? That would be equals to some volumetric change of that water, volumetric strain of water into volume of water, into initial volume of water, into volume of water, into volume of water. Yeah, initial volume of water. And that would be equals to 32 centimeter cube. So this is the equation we can have. We can have this equation. And for the volumetric strain of material, we can have that volumetric strain, that Hope strain and longitudinal strain. So we need to calculate those strains, and for that we need to calculate stresses. So I would say there would be development of some Hope stress, that is some extra pressure times d by 2t, and there's some longitudinal strain that is developed because of them. Some extra pressure has developed because of that 32 centimeter cube, that is PD by 4t. So if I have those values, I can write that. So I also know, I directly know that volumetric strain equals to PD by 4te 5 minus 4 mu. Do I know this result directly? I can use that. PD by 4te 5 minus 4 mu. I can write that. PD by 4te 5 minus 4 mu into volume. I have to multiply the volume of that material. Yeah. So if I take that volume, common, because if you take that volume outside for the two materials, if you take the volume outside, so we are left with this one. And similarly for the volumetric strain of water, we can have that equation of volumetric strain for the water equals to P by K, that is dou V by minus times, that is decrease of volume, that's P by K. So some pressure which has got developed, extra pressure has got developed, and because of that there is change in volume, that is decrease of volume, minus times. So P by K, so your K is, we already know that P by K, so we can write P by K into that volume, that total volume we can have, that's pi d square by 4 into some length of L. Now we have this pressure from this side, and this side we can keep that also common. We can keep that outside, that we need to calculate pressure P. And if I substitute the values of those parameters, I can write that diameter, we have diameter of 50 divided by 4 times thickness was 1.2, and value of E was equals to what we have, 100 gigapascal. So that is your 10 to the power 5 megapascal, and 5 minus 4 mu, 4 into mu. So plus some value of 1 by K. Value of K was 2000 megapascal. And that you have to multiply that entire term with this factor of pi d square by 4. Pi by 4 diameter square, 50 square into length of 1200 millimeter. So into pressure, some pressure of P, and that we have to equate with 32 into 10 to the power 3 millimeter cube. So we can get the pressure value of pressure equals to 15.17 megapascal. So this pressure has developed because of that extra volume of water added. Let's take the final problem. Let's take the final problem of this thin pressure vessels. We have a cylindrical vessel, and that the ends are closed. We say that the ends are closed. End is closed. This is your vessel, cylindrical vessel, thin cylindrical vessel, and we have that. It's saying that we are applying a compressive force, axial compressive force, of 55 kilonewton. You are applying this force on this material from the outside. So this is your axial compressive force, 55 kilonewton, and it's saying that the material, you have the tau max in that material, that is maximum shear stress it can have in the wall of that vessel, that is equals to 45 megapascal. and the dimensions of that is given that your inner diameter of that inner radius of that cylinder. That means there would be some cylinder, there might be some thickness, and there might be some radius, inner radius R, that is equals to 50 millimeter. Thickness of the wall is equals to 4 millimeter. So this is the data provided to you, and you need to tell that what should be the internal pressure that should be applied. So you need to say what should be the internal pressure. What should be the internal pressure? Internal fluid pressure. I don't know that value. So what should be the fluid pressure inside to be applied such that your tau max equals to 45 megapascal. If I say that you take any element, you take any point A from the inside of the material, let's say there is some point A, there's some point A, on that there might be some sigma x acting, there might be some sigma y acting, and we know that we have two stresses for the in-plane condition. For the in-plane stress condition, we have sigma 1 and sigma 2. One is your sigma long and one is your sigma hoop. Can I say that? But for now, we are talking about that we are having a sigma x and sigma y. We are having some value of sigma x and sigma y. Let's say if you calculate what is the value of sigma hoop, can you get the value of sigma hoop? That would be equals to that's equals to PD by 4T, PD by 2T, PD by 2T, PD by 2T. So if there is some section, let's say there is some section, because of that P in the x direction, there is development of that stress also PD by 4T. One is your longitudinal stress PD by 4T minus, because this is compressive and longitudinal stress is tensile. So if I write that, so if I talk about what should be the value of longitudinal stress, that would be summation of those two stresses we have along the long axis. Along the long axis, we know one is your longitudinal stress and one is your stress because of this effect of axial load P. So I would say there would be some internal pressure, but there is some external pressure also because of that P axial load. So I would say your sigma in the x direction is sigma long minus because of that sigma axial. I would say your long stress equals to PD by 4T and minus your load of P, capital P, divided by area. And area is on, what is the area for the section? Area of the section, we can say that is equals to 2 pi r into T, or you can say pi dt, because we directly say you can take you can take mean radius, but since we say that, then after that we say there is some mean radius pi d plus t into T. You have this area, mean area, then we say that T square can be negligible. So finally you got the value of area equals to pi dt. So you can write the area here, area equals to pi dt, similar to the area we have for the longitudinal strain. For the longitudinal strain also, longitudinal stress also, we say that T square is negligible. So you got that area equals to pi dt. So you have this equation along the x direction, sigma x. You have this sigma in the x direction. So you can write sigma in the x direction. We have some value of sigma in the x direction, and in the y direction we have some value of sigma. That we can take that sigma as sigma hoop, that is PD by 2T. So we got these two values, and we know that tau max in plane. Can we calculate that? Tau max in plane. Tau max in plane is equals to sigma hoop minus sigma long by 2, and we can write those values: PD by 2T minus PD by 4T, and plus capital P by pi dt, and divided by 2. Can we write that? Based on these results, we can write that tau max in plane is equals to PD by 2T minus PD by 4T plus PD by capital P. One is your small p, that's pressure, and capital P is your load of 55 kilonewton. And we need to get the small p, what should be the pressure that should be allowed, inside pressure allowed. What should be this value? We need to calculate. I would say that if I equate that tau max in plane with the 45 megapascal, I might get some value. So if I know the other values, we know the value of D. the value of D is equals to 100. Value of D is 100 millimeter. Do you know the value of D is equals to 100 millimeter? And I know the value of 2 also. I know the thickness also. Thickness is also 4. I know the value of capital P also. I know all other data I know, so I can get the pressure small p. So if I substitute those values, I will write 45 megapascal is equals to pressure P into what you call as diameter, that is 100, divided by 2 times thickness 4. Thickness of wall is 4 millimeter. Then we write minus times there is some pressure P into thickness of into diameter of 100 divided by 4 times thickness, plus there is some load of 55000 Newton divided by pi times diameter into thickness. Diameter is your 100, thickness is your 4, so you can get these values. And finally you can write pressure equals to, let's write this pressure as P1, that is 7.39 megapascal. So this data I got with respect to in plane condition, with respect to the plane of sigma hoop and sigma long. So I got this P1 corresponding to tau max in plane. Now if I calculate tau max out of the plane, tau max out of the plane, and I would say that is maximum of the sigma 1 by 2 and sigma 2 by 2, sigma 1 by 2, sigma 2 by 2. Yeah, out of the plane, because your sigma 3, we say sigma 3 is 0, so out of the plane for that sigma 3, because we are talking about plane stress condition here, because your sigma 3 is not acting there, so we say sigma 3 is 0, so out of the plane we have only that. You can take sigma max by 2 or sigma min by 2. So accordingly I would write PD by 2T divided by 2, and second one is that PD by 4T, and it has some minus of P by pi dt, P by pi dt, and divided by 2. So you can have these two. Out of these two values, you can write that should be equals to, but I don't know the value of P in these equations. I don't know the value of P, so I would write that, let's say this is some answer A1, there is some answer A2, so I have to equate that with the tau max out of the plane, So if I substitute tau max out of the plane equals to what we have, 45 megapascal. So if I equate that, I would say corresponding to A1, I will write 45 megapascal equals to P times diameter was your 100, 2 times, or we can say 4 times thickness. So I can get the pressure value of P equals to 7.2 megapascal. And corresponding to A2 terms, 45, equating 45 with that A2, I would write this should be equals to 45, and I can get the value of P if I substitute the values of, I would say P into 100 divided by 4 times thickness minus load of 55 kilonewton, by pi times D into thickness of 4 divided by 2. Yeah, actually the 2 should be divided for the entire. This is your that sigma 2 divided by 2. So sigma 2 divided by 2. So this term divided by 2, that should be equals to 45. So finally you can write that pressure equals to, from this equation you got a pressure of 21.4 megapascal. Now out of these three, which would you prefer? Out of these three pressures, which one you can allow for the material having tau, equals to 45 allowable. Tau allowable is only 45 megapascal. So if you want to take what should be the allowable inside pressure, fluid pressure, you can have for this material. So I would say I can take the minimum value of these three. I can take the minimum value out of these three. I can take the minimum value, that is 7.2. So finally I would say pressure allowed would be equals to pressure allowed equals to 7.2 megapascal for this material. So at this rate, So if I substitute that P equals to 7.2, if I want to calculate what should be the value of sigma 1 at this value of P, that is PD by, that is PD by 2T. So I can get a value of sigma 1 equals to 90 megapascal, and sigma 2 I can get value of PD by 40 minus some value of capital load of 55000 divided by pi times dt, d into t, diameter was 100. So I can get a value of sigma 2 equals to 1.23 megapascal. I hope you got the problem, that what the problem was saying. So you had that vessel, a cylindrical vessel, and you said that I'm applying a compressive force of 55 kilonewton along the long axis, and we know that along the long axis there is development of longitudinal stress, and I would say what should be the internal pressure that is allowed for the tau max? You can have tau max 45 megapascal. So we say that if there is internal pressure inside the fluid, there is development of long stress and hoop stress. I said that along the long direction, if there is sigma long acting, but there is also compressive stress of minus times 55 by that area of I dt. So we got that sigma in the x direction, and sigma in the y direction, I can say that's a major principal stress, sigma 1. That is what we can write that as PD by 2t. So based on this, if I equate that with the tau max in plane and tau max absolute, based on those conditions, I can get some value of P that's minimum. So minimum value would be we would take that as allowable pressure for that inside material, inside fluid pressure. So thank you for watching this strength of material. The strength of material is over. Hope you enjoyed our series for this strength of material. Thank you for watching. Thank you for watching.